Good morning. I wanted to show you an example of finding critical values using a t-table. In this particular example, we're given the alternative hypothesis, alpha, our confidence level, and the two sample sizes, N1 and N2, which we'll see are smaller sample sizes. Let's see, this particular problem, the alternative hypothesis, H sub A, is that mu1 and mu2 are not equal. They're not equal. And alpha is 0.05. N1 is 10. And N2 is 9. And we're asked to find the critical values. And we're going to do two parts to this problem. First, the critical value assuming of the variances are equal, and second, we'll assume the variances are not equal. And there's a little difference in how we do this. This really becomes an exercise in using a table. I have one in this particular book. You pull out, a lot of them are like this. Sometimes it's on the back cover or in the appendix of the book, or you can get probably infinite varieties of these tables online. So just be careful that you know what you're looking at. This one in particular has the one-tail and two-tail tests listed separately. They've done the division by 2 for us. So it's pretty easy to use. To use a t-table, you really only need two things. You need your degrees of freedom and your confidence level. We have that alpha 0.05, so we really only need to find our degrees of freedom. Then it's just a matter of looking up in a table. For the assumption that the variances are equal, the formula for our degrees of freedom is N1 plus N2 minus 2. So in this particular example, that's what, 10 plus 9 minus 2, 17. We have 17 degrees of freedom when the assumption is the variances are equal. So in our little table, we look out down to the row for 17 degrees of freedom and over to the column for the 95% confidence level. We actually need to know one more thing. We need to know what kind of test this is. Is it a one-tail or a two-tail test? Well, you get that from your alternative hypothesis. Since mu1 and mu2 are not equal, since that's our assumption, our hypothesis, this is a two-tail test because mu1 could be greater than mu2 or it could be less than mu2. We're only hypothesizing that it's different. If it was strictly less than or strictly greater than, then you have a one-tail test. But this is a two-tail test because we're saying not equal, so it could be not equal on either end of the distribution. So this is a two-tail test at the 95% confidence level, alpha 0.05. So we look up that row, 17 degrees of freedom, and the appropriate column for the two-tail test, and I get my t sub 0 equal to 2.110. Now remember, since this is a two-tail test, you're going to have two critical values, one on either end of the distribution. Fortunately, the distribution is symmetrical, so the other t sub naught is just the negative of the first one. Because we have one, our t distribution looks like this. We have a critical value. If we have a critical value over here, then the second one's on that side. And this is our 95% confidence level, and here we want our answer to fall in there. Okay, so what happens if the degrees excuse me, the variances are not equal. Variances are not equal. In this case, the degrees of freedom are calculated by the smaller of these two, the minimum of either n1 minus 1 or n2 minus 1. So that's going to be your smaller sample size that you're going to use to find your degrees of freedom. And for ours, n1 is 10, n2 is 9. So we're going to use n2 equal to 9 to find our degrees of freedom. And we get n2 minus 1, 9 minus 1, 8 degrees of freedom. And then once you have the degrees of freedom, you proceed the same way in your table. And I'm looking at the row for 8 degrees of freedom over to the column for my 95% confidence interval two-tailed test, 2.306. T sub 0 is equal to 2.306. Now here again, two-tailed test, don't forget you have a second one on the other side, which is the negative of the first one. So that's pretty simple once you understand the concept, pretty simple just looking it up in the table. Thank you.